Right, so in the last video I showed you a few examples of what you can do in a circuit wizard, whet your appetite for what you might do in an NEA. Of course, you don't have to do PIC design, circuit design. You don't even have to do electronics. You can choose your own Arduino design. But I really do think PICs are quite a versatile, powerful, certainly for the kind of level that you might be exploring, but also quite easy way of doing it. Um, Trouble with Arduinos, Raspberry Pis, they are object-oriented code base. Quite often they're based around a language called C, um, and it takes a certain type of brain to really understand. Whereas I find personally, from experience, the linear method of circuit wizard and using flowcharts, especially the visual idea of flowcharts, just works for simple brains like mine. Some people really kind of take to C-based programs and don't have a problem with Arduino. And the other really good advantage of Arduino is the huge amount of online resources that can help you develop projects. So it's no reason why you can't use any other system or do anything you want, but hopefully this will just give you a kind of um, stimulation, hopefully give you an idea of what you might do in your major project, your NEA. So in this example, I've got this old project that I did at uni at Brunel, and it wasn't by any means a large project. It was an interfacing project. Um, I probably did way more than I should have done with regard to this project because I flunked everything else during that semester. This shouldn't have been nearly as complicated as it was. I just got a bit carried away making something cool. So I had this idea of having this helicopter on a table. There's a servo in this counterbalance. So at the back of the pivot, the weight of this makes it take off really easily. So it doesn't need much throttle to take off. And then the servo will tilt the helicopter forward and backwards. The pivot in here has got little split rings, so it can spin round and round and round without getting any wires tangled up. And the idea is for this project we had it connected to a computer which would communicate with it, and it would randomly send an output. So one of these landing pads would be flashing, and you've got to fly to that landing pad as quick as you can. And it would just go around and randomly select these 4 different landing pads and time you to fly um, there quick enough. As well as that, either side of it's got these penalty pads, so you had to land squarely and correctly on it. You couldn't just kind of drop it straight down and hope for the best. Because if you got the penalty, you'd lose valuable seconds there. So all of this program was written in something called Pascal on the computer, and then connected to this bit of hardware. Um, so yeah, it's quite an advanced thing, way more advanced than it should have been in that project. But it's probably the kind of level, certainly with the power and flexibility of what PICs can do. It's a nice little example, NEA. Now, my top tip I've often discussed with Ted and Simeon about limitations of what you might be able to do in an NEA. I always believe that you should really try and strike the balance between doing something that ticks all the boxes and is fun and you get engaged with. Because I all too often see far too many students doing rather dry projects, and halfway through they're just bored of it because it's not really something that ignites their passion at all. However, doing something like this, you've got to kind of be quite smart about how you get all the boxes ticked. In other words, this has to be a marketable product, both in product design and design engineering. So you've got to justify its commercial viability. Now, if it's just a one-off kind of thing or a big toy like that, it could be a viable product, but you've got to understand the market. Now, this actual design idea, I kind of remember seeing it years and years ago when I was a kid in the Science Museum. It was actually a much more kind of mechanical example of how a helicopter flies, and it was pretty cool. Now, this could be just a prototype for a museum, a science museum. It could be a bespoke one-off product. That's fine, so long as you can justify it, identify the target market, explore and show your understanding of designing for a client rather than for yourself. So be careful if you're choosing something, pointless and playful, which I personally believe is a shame that you can't just go full whack and design something bonkers and fun. But you can, as long as you can justify its commercial viability. So yeah, that's the project that I'm going to recreate in Circuit Wizard. Obviously, it's all going to be kind of built in. It's not going to need to communicate with a computer. So this is it. And in the last video, I've showed you a few of the functions. The idea is we've got a basic program that runs round and round and round. So the program starts really well. The key thing here is choosing a random number, random A. So in this case, we have got 4 options, 0 to 1, 2, and 3. If it's 0, the program goes down this channel, 1, 2, 3, etc., etc. Remember I was talking about, now you could just be kind of waiting for an analog input, digital input when the landing pad is touched. Say, if output's 0, is waiting for input 0 to be pressed when the helicopter, I forgot to mention the metal skis of a helicopter. So basically, if it sends an output, it waits, is D0 pressed, and when it's pressed, it goes on to the next one. But the trouble with that is if, for example, the LCD is telling you to fly to A. Remember, we've got these variables here, so we've got a score and a time left written as variables here. Now this basically isn't live, so in other words, I've asked it to display the time. Now that time is changing every second. So what happens here is there's a wait command, and then the whole thing goes round and round until D0 is pressed. If it's stuck on that wait for 1 second and you land on the penalty pad, you don't want to kind of glance upon the penalty pad and get away with it. You want to be able to kind of make sure the user gets that penalty if they so much as touch it. So that's where we've got these interrupts. So in other words, it's always looking for a bad landing here. So yeah, we've got an until command. So until the correct landing happens, all of this happens. We're looking at a variable here. Is time down to 0? And if it is, it ends the game. So in other words, this channel here, this line goes back to the start and the whole thing starts again. Until D0 is pressed. When it is pressed, it goes back to here, which is basically this bit is call a new random number, and so many different things happen. I'll give you a little lowdown of what happens here. So there's slightly more advanced things. First of all, if you just had random A called, say we've just been on base 0, we come round, it's a 1 in 4 chance of base 0 being called again at this point. Now, as a playability kind of thing, that would be a bit rubbish if you've landed on a landing pad and it asks you to land on the same one. You don't have to do anything. So you want to make sure that doesn't happen. We've got 2 random numbers. So random A is the one that is called for this go. And then I should have been a bit more logical with my choice of letter variables, but F, I ran out of letters. S is the last random number called. So on the last one, so F becomes A. So if it's 0, we've just been through here, F becomes 0. And then when it calls a new random number, let's say it calls 0 again, it checks is A the same as F. If it is, go round again, get a new random number until you get a different one. So yeah, just little details like that make a better program. Other examples like that. C is the score. Now, if you get a bad landing, you lose a point as well. So, or you lose 5 points, sorry, in this case here. Now, what happens if you're already at 0 points and you do a bad landing? It goes round the clock and you go up to 200. You go, if you, it doesn't do minus numbers. So if you get -5, that's actually 251, I believe, or something like that, because there's 255 values on this chip. It only counts up to 255. So if it goes lower than 0, it goes around the clock back up to 255. So that doesn't look very good if you've got a mega big score by not getting any right and then getting a penalty. If that happens, so if it's higher than 250, then clear it. Just say it's 0. So you can't get a negative number here. What else happens? Well, let's say, just to make this game, I mean, say you're good at this game and you can fly around all the time. Each time you land correctly, you get a few more seconds on the clock, so you don't run out of time. Now, what happens here is that number, so let's say you get a bonus of 5 seconds every time you land correctly. But when your score gets rather big, that bonus time drops a bit, so it just gets harder and harder. So the score is, when the score's less than 5, you get 5 seconds added each time you get it right. When it's less than 10, you only get 4 seconds added, and so on until when it gets higher than 15, you just get 2 seconds. Okay, so there, here should be here, choose bonus. That's a little subroutine. Again, just tidying up the flowchart. That all of that happens just in that little subroutine there. So yeah, I think that's pretty much. Oh yeah, sorry, no, there's loads more to show on this. So yeah, we've got subroutines here. Obviously, there's kind of flashy lights, making it a bit more interesting. When the game happens, we've got game over. Gives you the total score, so on and so forth. Now, this is really just the program controlling the timer and the scoring and stuff like that. And it relies heavily on the output LCD to tell you what's going on as well. Simultaneously, we've got another chip I mentioned. This chip is working independently. You can have parallel processing going on Genie chips, but it's quite nice to have two doing the separate jobs and communicating. So you might notice on this one here, we probably haven't noticed because I haven't showed you, and I haven't drawn it out. So we've got so let's just make it big. So at the beginning it says game begin, press button to start. When the button's pressed, it will say get ready. The time is set to 30. The score is cleared. The clock is reset. 1 second, so it's saying get ready for a second and go. Flashlights. Something's missing. Where did I put it? Bear with me, sorry. Somewhere I've got another output. Lost it now. Basically, when the game starts, when you press the button to begin, the control circuit switches on. So our separate program, somewhere down the bottom here, is basically controlling the servo, which tilts the helicopter forward and backwards, and the motor, which is the throttle. So we've got two inputs, analog inputs, A0, both potentiometers. This A0 is controlling the pitch, so in other words it tilts the helicopter forwards and backwards. So it's reading an analog input, the full range from 0 to 255. We do a mathematical formula here, we scale it by 0.59. Now all that does is change, supposedly, sorry, there's two parts of it. So firstly it scales it to 0.59 and it adds 75. Now what that does is turns that 0 to 255 into the range that the servo is. So remember in the video that I showed you the different functions, the range of the servo is from 75 to 225. So what this does is scales it to 150, I think. So instead of 0 to 255, times it by 0.59, that becomes 0 to 150, thereabouts. And then add 75 onto it, and we've got this range here. So that's basically 75 to 225. So that full 0 to 255 on the potentiometer becomes the angle on the servo. And then the servo is just told to go to position A, which is the variable that we've just assigned the analog thing to be. So that constantly is adjusting the servo whenever it goes through this part of the flowchart. As well as that, the other variable resistor potentiometer A1 is just a straight assignment to variable B. Then when B is less than 10, the motor is off. Now I found actually I've been tweaking it a bit, and it's just off all the way up to one of these. I think we can check. Yeah, it's still off on that one. And then it just comes onto the minimum value there, and then a bit more there, and then full power that one. Okay, I might want to tweak these. I probably you know, adjust the input, the compare amount, but also adjust the output, just so that I can turn the throttle enough to be able to have it idling or something when you land, but not enough power to take off. Now this is all done in theory, and I've tested the electronics, but being on lockdown, I haven't been able to build this project. So yeah, all these kind of variables can be tweaked later on. Now I was saying this whole thing happens when can't really scroll off the screen here, when D6 is on. So on this Genie chip, again, I have drawn it out here, as well as this reset pin that I said you've got to have tied high on all these chips, we've got an input D2. Now this isn't actually joined onto this circuit, it's joined onto the other control circuit. Now I couldn't find that function somewhere, but somewhere or other is an output when the game begins. Don't know where it is. Maybe I've got a different version here. But basically, we say when the game begins, we say output. Let's say output 6 on this Genie chip. Goes over to the other one and becomes high. So therefore, the servo and the throttle are then activated. Not only that, we've also got a pulse as well. Like it's a parallel process going on. So in other words, we've got I haven't drawn it on this chip, but on the program it's there. We've got this pattern. Now all that is just a flashing light on the helicopter, continually flashing on and off. Just looks cool, but it happens independently of this kind of reading. So this is going round and round every time. There's no real kind of wait. It's just constantly going around, always updating the variable resistors. But whilst that's happening, we've got the helicopter light flashing, and we don't have to worry about that output on, wait, output naught. It's just constantly going on there. So yeah, that always happens whilst D6 is coming out of the other chip. Okay, so it's a nice way of having various different things happening. Now, if I've got the means, I don't know actually the means yet to be able to join these videos together, but I've got the hardware up and running. I'll just upload a little video of it working alongside this, because I don't think I can edit this video and join it on. So yeah, hopefully that is going to kind of inspire you whet your appetite to come up with something interesting and quite advanced for your NEA. Okay, thank you very much.